Imagine trying to hit a bullseye that jumps to a new spot every single time you fire. Frustrating and basically impossible, right? That is almost exactly the trap deep Q-learning falls into. The target the network is trying to reach is computed by the very same network being updated. So every adjustment shifts the goal, and the whole thing chases its own tail into oscillation and divergence. This feedback loop can wreck training entirely. The elegant fix has a wonderfully simple name, the target network, and it is one of the two tricks that made deep Q-learning work. Let's dig in. So how does a target network actually stabilize learning? Follow it one step at a time. Start with the need. In Q-learning with a neural network, you train the network toward a target, the reward plus the discounted value of the best next action. Something has to compute that target for every single update. Here is the fix. You keep a separate copy of a network whose weights are held frozen for a while, and you use only that frozen copy to compute the targets. It does not move around as you learn, so the goal you aim at finally stops running away from you. Now, the main network trains against those stable targets. Because the goal stays put between updates, the learning problem momentarily looks like ordinary supervised regression, calm and well-behaved, so training converges reliably instead of spiraling out. The network is finally aiming at something that holds still long enough to reach. Every so often, you refresh. Periodically, say every 10,000 steps, you copy the main network's weights into the target, or in soft update variants, you slowly blend them each step. The target keeps up, but only gently and gradually. So why bother with a second network at all? Here is the difference side by side. With a single network serving as both target and learner, the goal you aim at is produced by the exact weights you are changing. So every update shifts the target too, and the network chases its own tail, causing oscillations, divergence, and unstable training that often just falls apart entirely. This method keeps a separate target network whose weights stay fixed for a stretch and are used only to compute the targets. The goal now sits still between updates, so the network aims at something stable, and training becomes reliable, supervised-style regression that actually converges. That one change is what turns a diverging mess into a system that learns dependably. Strip it all down, and three ideas capture the target network. It is a slowly updated copy of the Q network. Same architecture, but its weights lag behind on purpose, changing only occasionally so that the values it produces stay steady while the main network keeps learning. It provides stable targets, so learning does not diverge. By fixing the goal the main network aims at, it turns a chaotic, moving target problem into calm, convergent regression, which is what makes deep Q-learning actually work at all. It is updated periodically or by slow soft blending. A hard copy every so many steps, or a gentle blend toward the main network each step, and its one knob is that update rate. Too slow and learning lags behind, too fast, and you lose the stabilizing benefit entirely. All right, let's lock in what matters. A target network is a slowly updated copy of the Q network, used to compute the learning targets so the agent stops chasing a constantly moving goal. It fixes a real instability. When one network computes its own targets, every update shifts the goal, causing the oscillation and divergence that plagued early deep Q learning. By freezing the target between periodic updates, the learning problem looks like stable, supervised regression, and training converges reliably instead of spiraling out of control. Together with experience replay, the target network is what made deep Q learning stable enough to master Atari from pixels. If reinforcement learning explained this clearly is what you have been after, there's a whole lot more of it waiting at standarity.com. Come explore with us.